All right. Good day. Welcome to this presentation. I'm Vukosi Marivate. I'm the Upside Chair of Data Science at the University of Pretoria, and I will be giving you my overview to large language models as, we've got to know them over the last few years. I'm a researcher in natural language processing, and this is just a talk I've been giving out throughout 2023. So this is the final version of it, and I thought I should just record the final version and make it available to everybody to be able to watch and listen to. And I do hope that it's very useful for people. And if you do find it useful, please let me know in the comments, or you can also chat if places that could have been improved. So I am at the University of Pretoria as the chair of data science and run the Data Science for Social Impact Research Group. But I've also co-founded the Deep Learning Indaba, which is a grassroots AI organization here on the African continent, and Masakane, which is also a grassroots natural language processing organization on the continent. I am a co-founder of Lelapa AI, a AI startup based in South Africa, and sit on the board of the steering committee of the Lacuna Fund, and I've also been a Harvard South Africa fellow at HBS. The lab at the University of Pretoria, we have a number of people all the way from research assistants to honors, masters, PhD students, some postdocs and senior members who are staff who mostly work 70% on thinking about natural language processing for African languages. And then the rest also do data science for society, or finding ways that we can use data science in health, in education, in energy, those types of things. It's been great working with all these people. And I think also today's presentation is just a combination of what we do within them. Now, we're going to go through very quickly the steps that I think you need to understand to really get an appreciation of the large language models that we have today, like Bard, like ChatGPT, Open Assistant, Llama, all those different things. First, we're going to think about what is natural language processing. So to think about this, we think about the applications or things that you use. So one might be the first time that you ever used natural language processing was a spam filter. You got your email, and then there was this little folder with spam, where all of the nasty stuff goes, and then also using a search engine where you type in. But we've had things like virtual assistants, chatbots, translation systems that are available. A good way to then really think about this is maybe on input-output, like just like machines or computers. So here's an input, Dumela Maholo, output being greetings elders. This task would be translation. It was one of the worst days of the year. The output being negative, there's a sentiment analysis, opinion mining. Who's the president of South Africa? So Ramaphosa being the response there. Question answer, reading comprehension. You have received the credit of that by e-filing. Suspicious might be spam detection. Then you have this paragraph that you have here, and then you might go and then summarize it. And then you use the summary that's just one sentence. So we are going to go through this by developing some tools. So let's develop our first tool. First, to do that, you need to get machines to understand language, right? So you need features. So features are these things that you can represent words. In this case, we're going to be talking mostly about text to a machine. So you can treat words as atomic features. Here, let's say we have a new language that only has these five words: car, house, tree, drove past. Right? So one approach is to use the one-hot vector. So a vector is just a mathematical representation that you can use. And now what you can have is a car can be a vector of size 5, but then with one being only in one of the areas. So 1, 0, 0, 0, 0 means car, 0, 1, 0, 0, 0 means house, just like that. Tree is 0, 0, 1, 0, 0. And then now you've got all the 5 words now have this representation in these vectors, and the vector is orthogonal, meaning like, each vector just represents one thing, each index in there represents one thing. How can we make sentences? We can make them maybe from combinations. So car drove past tree house just becomes 5 ones because every word is in there. But we do lose something in this case. We lose the order. So we don't have that ordering that is connected with us. This representation also doesn't give us things like semantics. You could bring back the ordering by doing concatenation, where now you just take the representation for car, take drove, you put next and passed just like that. And then what you see here is that now you have the order, but now you have this explosion of the size of how you represent that. This representation here was compact, but you lose order. This representation now has order, but now you need to store bigger pieces of information. So no free lunch kind of on there, but this could be useful anyway. So we're going to build up a tool for natural language processing. In this case, we're going to build a search engine. So in this one, or what we call document retrieval. The task, you have many documents. We call this a corpus. You have the search term Q. It's made up of these symbols or words, and you want to return documents that are relevant to Q. So the simplest thing you can do is count how many times each symbol appears in every document. So the thing that we did there, now you take the full document and you represent it and you count. Instead of just a 1, you can also put how many times you see that word in that vector. Then you return the documents that have the highest count combined of the search term that you have in Q. So there we built the search engine. And the thing that's important for us, try to figure out what did I press here. Yeah, much better. By doing this, what you have is we've thrown away, as you said, like that, the sequence and the semantics, but we just counted these words, and that's enough to build up our first kind of document retrieval. But because we've thrown up, all we do is counting these words, and we don't care about the order, it's called the bag of words model, because it's the same as taking some, a document, throwing it inside a bag, and just removing words one at a time and just counting them. You don't really care about where they were, but then you just care about their how frequently the words appear. Also, a feature does not necessarily need to be a single word. It can be combinations of words, like a bigram, which is 2 words. So today was becomes one feature, was a becomes another feature, or trigrams to was a, the types of things. So you can expand through that, and it can assist you in finding things like phrases instead of finding kind of one word. The other thing is, remember we showed words like these words are not really informative, and what you might want to do is actually count less, make them count less, and this is where TF-IDF comes in, term frequency and verse document frequency, where if a word shows up a lot in all of your documents, what then happens is that this term here reduces the overall term, and we multiply how many times you've seen that word by the inverse of how many you've seen that word in all of the documents that you have. So words that we tend to call stop words that don't really have information, then we'll have TF-IDF scores that are very low on there. So we can fix that. So, right, we built one feature. Now let's think about the second thing we can build now for natural language processing. So the second one, hey, we're going to do language modeling, and now we're going to think about that semantics. So what we want to do is estimate this function here. So the probability of a word given a sequence of words that have come before, so probability of W of t plus 1, given that you've seen 4 words before, all right? So you want to then estimate this probability function, and what's interesting about it, it's very useful if you can do it, because if you've got this probability function, you can then try to sample from it and then generate the next word. So what does this mean? You've seen this before. It actually does have a layman's name. This is autocomplete. So if you have autocomplete on your phone, you have it in your email, where you type in some words and then it starts predicting the next number of words that you should actually put in there. This is exactly how it comes from. So we can then build a language model, and it's useful for generating text, and we can do what's called a statistical language model. Right? And yes, we can do this, and you don't need the full sequence. You can just take the last 4 words, the last 3 words, instead of having the last paragraph, for example, on there. So we're going to do this as a live demo. So I'm going to go in there, and there we are. Make this a little bit bigger. So here, we're going to start and building this simple language model of ours. So you've got some data here, and the data is going to be a pair of sentences. This is a beautiful day. It is a beautiful day for ice cream. What we're going to do is now go through all of the data and take the sequences in trigrams, so in 3. So find 3 words in this document. So this is a beautiful, beautiful day, full stop, day, full stop, it, like that. So if we do this, this is how the data looks like. You have sequences, none, none, this. The reason we have a none is that there was no word before this. So what we're going to do is pad it with this new token that we just call none on there. So we can visualize this and also start counting. How many times have we seen none, none, followed by the word this? We've seen that once. And then we can do this for all of the sequences we've seen. And you can see none, none, followed by this one time, none, this, followed by is one time. But here, there's something interesting. Is a one time was followed by beautiful, another time is a was followed by good. So there's half a chance, given our data that we have, when you see is and a, sometimes it's followed by beautiful, and then the other half, the other half of the time, it's followed by the word good. So you can now change this into a frequentist probability where you have that there's a 0.5% chance that you go from is a to beautiful. There you go, and there's another 50% chance of going from is a to good. And now you fill in this what we call a probability matrix, where you see on the rows there are the pairs of words, and then on the columns is what the next word is supposed to be. For most of them, they're just ones. I mean, most is zeros because we've never seen that data. Some places you have ones. And then here for is a 0.5 beautiful, 0.5 good. Great. Now, with this, we can actually now generate some text, right? So we can just take none, none, and say what's the next word is supposed to be. We've only seen none, none being followed by this, so that will be the first one. But you can see here, sometimes it generates, this is a beautiful day, is a good day for ice cream. If I run it again, this is a beautiful day, it is a beautiful day. Remember, it is a, when every time you see is a, it might go beautiful, the other time it might go good. So that's our thing, and it can keep on generating over and over again. We can get more data and much larger data. So here we're going to download some data from a South African government newspaper that they gets published to provide information to citizens. Here it is. I downloaded one that's aligned between isiZulu English and isiZulu, but then we'll use the English just for now so that we can all understand. And there you've got 2,300 articles that are available. Oh, 2,300 sentences, not articles. So we can do exactly the same thing we just did with that simple 2 sentences. And by doing that, now you've got this larger data set, and then we can actually do the generation. So there, the program is unique, that it takes a village to raise a child. That's just generation. I can do that again, according to the peer, it stops. I can then continue again. The findings of a better world over and over again. It will just start and then start generating and continuing. So hopefully that's giving you a bit of ideas here of like, oh, that's how language models work. You have to estimate this probability function, and if you have it, then you can do this generation given a couple of things. So that's what we have, and then you can also estimate what the probability of seeing the data that you've just seen there actually is. So that's one more thing we have done now. So let's now go back and let's put it on. There we go. Cool. Thank you. So we've now built an n-gram language model, and thank you to NLP for Hackers. That's where that example came from. I just adjusted it, and it will be also available at the link to that notebook. You can play around with it. Is available in the video description as well. Okay. So what have we done so far? We've represented the text. We've understood that you can have term frequency, how many words show up in a document. We've done TF-IDF, and then we built a search engine, and then from there we built a statistical language model, n-gram language model. But before we go to the next part, the thing we need to now get to understand is actually what's machine learning, because that's the thing that's going to allow us to scale and do some interesting things on that. So first, we start what's AI. AI in a classical definition is that you have an agent, machine, it exists in some environment, it takes action to achieve some goal. So here is one of my daughters. She's looking at one of our robot vacuum cleaners in the house. It's a machine. It lives in the house. The action it can take is that it can move around, it can vacuum, and the goal that it has is to actually keep the house clean, right? So that's an artificial intelligence in a way. Machine learning is a subset of AI that deals with the machine learning patterns from data. So now let's look at this again. So let's say you have 2 dots that show up on a plane, on this flat surface. One is red and one is blue, and we're interested in where they land. And now I say, if I give you a new dot that doesn't have a color, can you then, meaning I landed anywhere in this area, can you please tell me what color it would be? Can you predict it? So what you could do is learn that that's like, a simple decision function or a boundary that says anything in the simplest thing I can have is this line that sits in between. because it's equidistant and I'm making the least assumption about my data if I only have these two data points. Anything in the future that lands on the left, I'll predict that it's red. Anything that's in the future that lands on the right, I'll predict that it's blue, right? So now I've learned that pattern from the data. And yes, life is more complicated than this, and your data could be more complex like this. And what happens is that also your decision boundary becomes more complex. And here, anything that's above that line, I'll predict that it's blue. Anything that's below that line, I'll predict that it's red. And yes, in this case, I haven't done things like what happens if there's one red dot in here, in between the blue dots and all those things. So there might be some error, but this decision boundary is still the least error that you have on there. And you can go read up a little bit more on that. We can then make the jump in to thinking about modern AI or modern machine learning, where you have these huge deep neural networks, and the things that you can get from, as a direct thought, a move from that is that now you can have these systems that you can give in a lot of images that they've seen before of dogs and cats. You give them the image, and then they can predict that what's in the image is actually a dog and not a cat, right? And these are now models that some of them are deployed on your phone. You can just, you can go to a gallery and look for pictures of animals, and you find all the pictures you've taken of that specific animal in the past on them. And the example I've given is also supervised machine learning, where it's already given input and output. So you give it examples of the input, like the image here, and then the output would be the thing that you're trying to give it examples of. Oh, you say in this picture there's actually a dog, or in this picture there's a cat, and over time it learns that pattern. Why machine learning? In the past, if you had to do this, you would have to write all these specific instructions or recipes of being able to explain what is the data that is being fed in, what kind of things in that data should look like a dog. Like a dog will have ears, will have a snout in a specific way, a specific size, and thinking about that from a pixel level. But with machine learning, you just feed the model, the learning algorithms, the data, and with enough data, they produce models that are useful for that task instead. All right. So this is how we get closer to large language models, right? So now we've got representation of words, we've got machine learning. Can we now do language model at a bigger scale? And yes, we can. And one of the things that was very important is thinking about mass language models. What this was we can now turn that problem of the statistical language model into a machine learning task. So you can then take some data, take some sentences, remove a word from the sentence. Instead of it being input into the machine learning algorithm, it can now be output. So you put a mask. So that's what happens. So you take the sentence, you remove a word from it, you say there's a mask there, and then you put the eating and you put it on the other side. And now you say, I'm going to train this machine learning model to predict the word that I've removed, kind of on that. If you do that, now the model that gets created is a model that now predicts words given sentences on there. So you're doing almost the same thing that we did with the statistical language model or the n-gram model, but now you taught it using machine learning. And the thing that's very interesting about this is, remember, you see how this text was just some general text and we removed the mask. You could go to a place like Wikipedia, get all of Wikipedia, prepare it in this way, randomly remove words on sentences in many, many different ways. And now you create this Roberta language, or this language model that's sitting as a mass language model. And this has really been now we're in 2017 with the BERT paper that really gave us this this reusable model, because what you can do with BERT, for example, is that you could take Wikipedia, books, train the model, and then this model now can predict that next word thing, but it also gets a representation of actually the language that you've been training it on. And from there, you can take the pre-trained model and now fine-tune it for your final task. So the final task here, for example, is then training a classifier that can classify spam or not spam. And you would have actually seen this a bit during that period, because for Google, where the BERT paper comes from, they actually implemented this in their systems. And you could see it both in the autocomplete on their email app, and also new ways that you could actually see search engine responses and spam classification, those types of things on there. So this is a great kind of jump on. So if you've got this, one of the things that you can do now, instead of doing spam detection, you could do things like question answering. So there's these data sets, for example, like Stanford question answering that has I think 100,000 question and answers. You have another one here like Trivia QA that also has 95,000. questions and answers, and you can now take this pre-trained language model that's been pre-trained on this next word prediction task, and then fine-tune it for question answering, because then it can generate these responses, right? And there's also an example here about alpaca data, and you can see here that's what the input will be: give 3 tips for staying healthy, and then the output that you want the machine to do is write out these examples on here. So now you keep on giving these now pre-trained models and fine-tuning them on question answering, and now you get them to answer those questions. So this is great all in all, but then how do you make sure you can make that the models actually respond in a way that is a human expects, right? So if you just let the models just respond, some of the things that they might say might be not said in the right way. There might be areas that you read people might find offensive. So what then happened is that last year, so in 2022, there was this work that came out of OpenAI on reinforcement learning for human feedback, where now you can also provide, on top of now you've done the pre-trained model, you do the question answering task, and then now what you want to do is do this alignment. So you're trying to now get human feedback from what the machine generates when you give it a question. And then this allows then a labeler to, or a human to ask a question, get a response, and then tell the machine whether the response is good or not, or rank how good the responses actually are. And then if you keep on doing this with enough data, it then changes the model to now generate things that are much more aligned to what the preference of who the labeler actually is. So this was now the Instruct GPT paper, and really this is the thing that pushed us through the current proliferation of language models, because that's really where these chat models became much more open kind of to the public, because they can do this. But to understand, when we were in December 2022, there were many language models, the ones that, and there have been many more since then. So it wasn't just that, it was just one model came out. It's that there's been all this march of building these language models over over years, especially since we looked at the BERT paper. So if I look at this evolutionary tree here, so you can see BERT will be 2017, the BERT paper, and then you see there's the BERT paper there, and then you start noticing all these different types of way of building language models. And where we are now, you've got the GPT-4s, you've got the BARDs, the Llamas, the Llamas 2s, kind of like that. So it's a very interesting, very fast in retrospect development that we've had in these areas. This is going to be a little bit more dated, but one of the things that was interesting with GPT-4 in terms of examples was showing how it can take tests and how it was doing well in some tests, and compared to human, how humans were actually performing within these tests. And we can see this march of really these models getting better and better and better. And every time there's new new models, they then show these benchmarks of how well they're going. But a challenge that though does come with some of these models is that in the reports that they have on how they built them, there is a lot of information that is not disclosed, and especially there's lack of disclosure about the data that comes in. This is very important on a number of fronts. One, it's what do the models really kind of encode, or what it has is inside the model itself is very important. So if we don't know where they're sourcing most of this data, you don't know where the blind spots are going to be. So this is going to be a huge challenge for people to really trust them completely. Not that you should in any way, because of they kind of generate things they've seen before. But at the same time, we should be very careful in thinking about this. Another point is there's been this rise then of the open language models, your OpenAI, ChatGPT, some of the models from BARD. It's great that they're there, you can use them, but they're not open. You can't really go and get the model and see the weights that are learned inside, or even just download it and use it in whichever way, or continue training it or fine-tuning for other things. And the great thing that's happened is this big push. This is like looking back about 6 months ago, where you had llama, alpaca models being available, and these really push other people to be able to test, see what really goes in, and really be able to share. And then this has been great. And at the end, I do believe also personally that open source will win. There was this experiment that went on. It's now off, like where now you had, for example, Open Assistant that was created from Llama and then could be used by anybody. And you didn't necessarily need to have the big models as well. So what does this mean as we now go towards the latter part of this presentation, right? Many things have happened here over the last year. We, though, can learn from parts of our past, and in this case, the Hitchhiker's Guide to the Galaxy, where asked, can you give the answer to the ultimate question of life, the universe, and everything, to this computer called Deep Thought. After several million years, the computer comes back and says the answer is 42. 42 yells one of the characters, is that all you have to show for 7.5 million years of work? And the machine responds and says, yes, I checked it very thoroughly, and that is definitely the answer. The problem, to be quite honest with you, is that you never knew what the question was. What is happening right now is there's a lot of what, like, going back to learning about Google Foo, now we've got this LLM Foo, or the prompt engineering, where for much of this year has been this work, like, of how do you actually prompt these systems so that they give you responses that are actually useful on their way. And we are doing that right currently, and we're still trying to figure out, the designers are trying to figure out what's the best way to get the, responses that are useful for the rest of us. At the same time, as I said, we don't know where the source of the information that they have completely is, especially these big closed models. Do they credit where the data comes from? Did the people who created the content consent? Were they compensated? And at the same time, aren't we also capturing the worst of the internet? And that answer is yes, right? We don't know, like, what kind of things could be done with these models. We're trying to still evaluate them, but it can't just be from an input-output where you just ask it and you get out. We need to know how they were trained, right? The other thing is you have to be careful that they're just labeled almost like as these all-knowing machines. They are not, and they also don't represent information seeking. That you still need to understand where the information came from, synthesize that source, and then be able to come up with your understanding and your own opinions on there. So it's very hard because people are thinking that they do that, and we've seen lots and lots of examples where that just really fails. Another point here is, remember, for a lot of these very large models, they're going all through the internet, scraping websites, taking as much of this content, and then trying to compress it inside the model, right? Because the model is not the size of the internet, it's smaller. So because of that, they then have these blind spots because of the compression. Remember, if you take an image like a JPEG, and what you do is you try to reduce its size. So let's say it was 5 megabytes, and now you're going to make it 1 megabyte. You have this lossy compression. You lose information. That's why sometimes the JPEGs become a little bit more blurrier if you then go in and compress them. So ChatGPT, these are actually a blurry JPEG of the web. And you see this in a number of things. So one, there's been these questions of like, hey, we try to ascribe these models like human features, they are not humans. And then what kind of things actually are going on inside these models? Like the paper, this article here on this conversation of the guided feedback is limited, where you had a chatbot really leaving a journalist unsettled because of the type of conversations they were having. At the same time, let's think about that compression. Here's this test that you could do earlier this year. You would ask these models, what weighs more, 1 kilogram of feathers or 2 kilograms of bricks? And the model will respond and say both sets of objects weigh the same time, 1 kilogram by 1 kilogram, right? And how would this actually, why was this happening? Is that partly on the internet, there's many of these logic games of what weighs more, 1 kilogram of feathers or 1 kilograms of bricks. And then obviously they weigh the same because I've already told you how much they weigh. They weigh the same thing. But because of those blind spots, right, that I think it doesn't read the one or the two, really. It just went on and just said 1 kilogram is equals to 2 kilograms. And then it goes on with that. And that was ChatGPT. We could do this with earlier Bing. And then in this case, it answered right on the 9th of March. And then 2 weeks later, it answered wrong, right? The same question. Here was Bard earlier in the year. and it was also having the same problem. This was Llama, and this was Open Assistant. They all had the same kind of problems at the beginning of the year. I'm pretty sure now most of this has been fixed with different ways to try and fix these things. But then it was very, like, very interesting kind of failure of this simple logic question. And this then must get you to think, for example, that you have people who are like lawyers using these systems to generate arguments of like, how does this work? Because they can generate completely false information. This is one case here that happened in South Africa where the lawyer ended up, the LLM ended up generating arguments that were completely, like, the references were false. They didn't exist. Here's and then the judge, when they think about the amount of time that it took the other lawyers to go try and track these cases that were referenced, and then they actually found out later that they didn't exist. What then about low resource languages? This is another problem that these types of models have. So here's some work that we did at Lilapa. Now, just looking at prompting these models earlier in the year in isiZulu. Here's one from one of our contractors saying, hey, count from 1 to 10 isiZulu, and then the response being Q1, Q2, Q3, Q4, which is not correct. Then translate from English, isiZulu to English, kuyabiza ukugibela ibhanoyi, which actually means it's expensive to go on an airplane. But then there's the response, he insults him by calling a coward. Very, very much with confidence, like that response, and it would be wrong. Here's another one trying out Open Assistant. Here's count from 1 to 10 isiZulu, and then these are actually incorrect, and like all these words for the people who might know isiZulu. My hypothesis here is that there are these websites where they try to interpret your dreams by the things that you see. So here they were explaining in isiZulu specific things that you might see and what numbers they might represent on there. And this is still wrong. This is not 1 to 10 in isiZulu on there. So it then becomes this thing of who then gets counted inside these models, right? And you can now see this, for example, in this work where it shows the data sets that are used in natural language processing, where they tend to come from, and just with an exaggeration of the globe. And you can see most of them are coming from North America, parts of Europe, other major parts. So they don't represent most of the world. The majority of the world is not represented in here. And as such, this will create lots of challenges on them. There's some work from Dr. Sasha Lucioni, who shows here about, hey, we have these things that we're seeing on the surface of an iceberg, but we don't see all these other things that are below, right? Of that in these models, how they're built is important, what kind of biases that they have, how the copyright issues, the energy inefficiencies or any energy used on there. These are all the other things that we should really also be thinking about and finding ways to then battle with as time goes on. So wrapping up, on our side at the university, at the Data Science for Social Impact Research Group, we built other models, for example, Pua Berta here, which is a model for Setswana, and thanks to my collaborators on here, it's much smaller, but it's just there to get us to preserve our languages and also make tools that are available for other researchers to be able to use. We are working on all South African languages and also other languages across the continent. We've also worked on ways to deal with smaller amounts of data, like doing augmentation, some work with Catherine Gitau, and we try to deal with the data that we have for our languages that is not as big as English or French or German, but we can still do some interesting work. You can join us, and every year we run a seminar series called Data Science Society Seminar Series, a webinar. And it's been great to have it and have people really join us and see what actually is going on within there. We are thankful for all of our collaborators and in this work and also in the past, and also very thankful for all of our funders. There are more than this, but then it really gets us to do the work that we do and allows us to really explore this space and work to make it better for everyone. You can subscribe to our newsletter. We'll put this in the video description, and we hope to see you in the new year. Thank you, and I hope you did enjoy this. There's a little bit of a joke at the end of 2022. I was complaining that I don't want bigger LLMs, and obviously 2023 changed it. I don't think we did leave crypto AI in 2022, but we do still have that inflation. So thank you, and I hope you enjoyed this. And yeah, look forward to interacting with you more in 2024.